嗨，你们好，贺三、阿明。
很好，老师，你呢？
In the previous classes, we have talked about our sixth chapter, architectural design, and precisely we have talked about architectural design decisions, architectural views, architectural patterns. For the architectural views, we have talked about the well-known 4+1 view model of software architecture. Do you remember? The well-known 4+1 view model of software architecture. Do you remember these four? What stands for four and what stands for plus one? Yeah. Well done, Saji. And what else? Logical view, process view, yeah. Development view, yeah, exactly. Perfect for the four views. Thank you, Saji. And we have four views and plus one. What does it stand for? What does plus one stand for? Saji has perfectly listed the four fundamental architectural views. Yeah, not view, but that is, we have these four fundamental architectural views as said by Saji. And these four views, they are related using use cases or scenarios. That's what plus one stands for, use cases or scenarios to relate these four views. That's the 4+1, the well-known 4+1 view model of software architecture. And later we have introduced some architectural patterns. We have introduced five architectural patterns, if my memory is good. Do you remember these five architectural patterns? Yeah, I have seen three patterns till now. Yeah, four. The fourth one is appeared. And Hosan has listed, Hosan has listed for the five completely. MVC, we have MVC, model view controller, architecture pattern, repository, layered architecture, server client, pipe and filter pattern. Yeah, perfect. Thank you very much, Hosan, Sajie, Roy, Ramnak. Yeah, these are our five architectural patterns. In this class, we'll begin to see some different things as application architectures. Application systems are designed to meet an organizational need, and all business have much in common. Their application systems also tend to have a common architecture that reflects the application requirements. In fact, for all businesses, they have many commonalities, like they need to hire people, they need issue invoices, they keep accounts, and etc. So we have business operating in the same sector use common sector specific applications. Therefore, as well as general business functions, all phone companies, they need systems to connect a phone, manage their network, issue bills to customers, etc. Consequently, the application systems used by these C businesses also have much in common. So as we have said here, businesses have much in common, and their application systems have a common architecture too. A generic application architecture is an architecture for a type of software system that may be configured and adapted to create a system that meets specific requirements. Yeah, the commonalities of businesses and application architectures. These commonalities they have led to the development of software architectures that describe the structure and organization of particular types of software systems. And application architectures encapsulate the principal characteristics of a class of systems. For example, in real-time systems, there might be generic architectural models of different system types, such as data collection systems or monitoring systems. Although instances of these systems differ in detail, the common architectural structure can be reused when developing new systems of the same type. Yeah, we have as we are software and designers, we can use models of application architectures in multiple ways. The first one is we can use it as a starting point for the architectural design process. If if we are unfamiliar with the type of application that we are developing, we can base our initial design on a generic application architecture. Surely, this process will have to be specialized for the specific systems being developed, but it is a good starting point for design. Second use of application architectures may be as a design checklist. If we have developed an architectural design for an application system, we can compare this with the generic application architecture. We can check that our design is consistent with the generic architecture. We may also use application architectures as a way of organizing the work of the development team. The application architectures identify stable structural features of the system architectures, and in many cases, it is possible to develop these in parallel. We can assign work to group members to implement different components within the architecture. So we use the application architectures to organize the work of the team. We can also consider the application architectures as a means or a way of assessing components for reuse. If we have components we might be able to reuse, we can compare them with the generic structures to see whether they are comparable components in the application architecture. We may also use application architectures as a vocabulary for talking about application types. If we are discussing a specific application or trying to compare applications of the same type, then we can use the concepts identified in the generic architecture to talk about the applications. So you see here we have different ways to use our models of application system application architectures. In fact, there are many types of application system, and in some cases they seem to be very different. However, many of these superficially dissimilar applications they actually have much in common, and thus they can be represented by a single abstract application architecture. Here, we will focus on two types of application. We focus on the transaction processing and the language processing systems. For the transaction and processing systems, there are database-centered applications that process user requests for information and update the information in a database. These are the most common type of interactive business systems, and they are organized in such a way that user actions can't interfere with each other, and the integrity of the database is maintained. This class of system includes interactive banking systems, e-commerce systems, information systems, and reservation systems like booking systems. For the second type of is the language processing systems. Here, for language processing systems, there are systems in which the user's intentions are expressed in a formal language, such as Java, Python, etc. And the language processing system processes this language into an internal format and then interprets this internal representation. We have the best known language processing systems as compilers. With compilers, we can translate high-level language programs into machine code. Yeah, however, language processing systems are also used to interpret command language for databases and information systems, and markup language such as XML. Yeah, here we have chosen these two particular types of system because a large number of web-based business systems are transaction processing systems, and all software development relies on language processing systems. And now we'll see these applications in detail. For the first one, transaction processing systems. Yeah, in fact, these kind of systems are designed to process user requests for information from a database or requests to update a database. Technically, a database transaction is a sequence of operations that is treated as a single unit. Yes, when we talk about single unit, we all see a notion. I think perhaps you have already seen it in other courses. The tiniest fundamental unit. And in detail, when we execute, when we have some operations with this atomic unit, what kind of characteristics? Chemistry? That means this word has many domains. Okay. In fact, I think in your course, I'm not sure if you have already the lecture operating systems. Have you already had it? Operating systems. No, not yet. Okay. There normally you have something related to atomic unit. With an atomic unit, that means all of the operations in a transaction have to be completed before the database changes are made permanently. That means we consider all the operations as a total, as a whole. Yeah, either we can all execute them. We can execute all the operations, or neither or none of the operations will be executed. This is important for transaction processing systems, as this will ensure that failure of operations within the transaction does not lead to inconsistencies in the database. Yeah, in fact, we'll have see some examples later. You will see really it's very important, this characteristic. From a user perspective, a transaction is any coherent sequence of operations that satisfies a goal. For example, find the times of flights from London to Paris. You see here, if the user transaction does not require the database to be changed, then it may not be necessary to package this as a technical database transaction. You see, to book a ticket or a flight, if it is very important in this case, as if we yeah when we consult, if there's only one ticket left, then we book it. You see, we have only two possibilities. That means either we'll finish the whole process of booking. That means we'll complete our personal information. We'll pay for it, and then the how to say the left ticket will be zero. All these activities either they will be finished together or they will not happen. All these activities will not be happen. Is it clear? Imagine if
Now, please repeat again. I didn't quite get it.
Okay. Let's take an example of booking our ticket. When we book a ticket, we have multiple steps or multiple activities. We need to, firstly, we consult the number of tickets left. Then we need to book it. We have to complete our personal information. We have to pay for it, and then the information will be changed. That means the number of tickets left will be changed. All these activities, either they will be executed together, all of them will be executed, or none of these activities will be executed.
I understand.
It's okay?
Now it's okay.
Okay, yeah, because with this system, we can ensure that if we fail to complete the information or something else, we will not lead to inconsistencies in the database. That means, we will not change the number of tickets left. We will not pay for it if we don't complete the information. We consider all the activities as a whole. That's the atomic unit, and it's very important for the transaction processing systems. As with this system, we will not lead to inconsistencies in the database. Yeah, we have also a very important example of a transaction. It's when a customer requests to withdraw money from a bank account using our ATM. This activity involves getting details of the customer's account, checking the balance, modifying the balance by the amount withdrawn, and sending commands to the ATM to deliver the cash. You see, all these activities or all these steps, we have to finish we have to complete all of them before before finish the transaction. Else, the transaction is incomplete and the customer account's database is not changed. You see, that's why we say transaction processing systems are important, because in many business situations, we need these properties. And users make asynchronous requests for service which are then processed by a transaction manager. Transaction processing systems are usually interactive systems in which users make asynchronous requests for service, as said here. And we have a figure like this to illustrate the conceptual architectural structure of transaction processing applications. You see, at first, a user makes a request to the system through an input or output processing component. As we said, an ATM or machine or something like this. The request is processed by some application-specific logic, and a transaction is created and passed to a transaction manager, which is usually embedded in the database management system. And after the transaction management manager has ensured the transaction is properly completed, it signals to the application that processing has finished. Yeah, you see, this is the conceptual architectural structure of transaction processing application. This figure is a detailed architecture of an ATM system. You see, transaction processing systems may be organized as a pipe and filter architecture with system components responsible for input, processing, and output. In this banking system, we allow customers to query their accounts and withdraw cash from an ATM. The system is composed of two cooperating software components, the ATM software and the account processing software in the bank's database server. The input and output components, they are implemented as software in the ATM, and the processing component is part of the bank's database server. Yeah.
Why isn't validate card underneath the process or part of the banking's database server? The validation of the card.
You talk about this one? Yeah, you talk about this one, validation card.
Yes, Laoshi.
Here you see, as when we go to, when we work with our ATM, we need to offer our account ID and we need to validate the card. That means we need to tap some information like the password, something like this.
Oh, that's what it means. Okay, Laoshi.
Yeah,
I understand.
And after this like authorization, then we can select corresponding services like query account, update account, and these activities need to be communicated with the database. Later, after these processes, we may get some outputs like print details of your account. We will return our card and we will dispense cash. That's the architecture of this banking system to illustrate the functions of the input, process, and output components. Is it clear for the moment?
Laoshi, it's clear.
Okay, yes, thank you. Clear. So we'll continue. This is the first type of application we introduced for the application architectures. Now we will see another type, which is information systems architectures. It's not it's not the focus of our two types, but it's a frequent system too. Information systems have a generic architecture that can be organized as a layered architecture. And these are transaction-based systems, as interactions with these systems generally involves database transactions. All systems that involves interactions with a shared database can be considered to be transaction-based information systems. And an information system allows controlled access to a large base of information, like a library catalog, a flight timetable, or the records of patients in a hospital. So increasingly, information-based systems are web-based systems that are accessed through a web browser. As said here, we may organize the information systems as a layered architecture. We can include 4 layers here: the user interface, user communications, information retrieval, and system database. This figure shows a very general model of an information system. In this system, it is modeled using a layer, as we said, it is modeled using a layered architecture or layered approach. The top layer supports the user interface, and the bottom layer is the system database. The user communications. This layer handles all input and output from the user interface. And the information retrieval layer includes application-specific logic for accessing and updating the database. As we may see later, the layers in this model, they can map directly onto servers in an internet-based system. This one. This is an example of an instantiation of this layered model. It is the architecture of our previous example, MHCPMS, that is Mental Health Care Patient Management System. Don't forget that this system maintains and manages details of patients who are consulting specialist doctors about mental health problems. You see here we have added detail to each layer in the model by identifying the components that support user communications and information retrieval and access. You see here the top layer is responsible for implementing the user interface. And in this case, the user interface has been implemented using a web browser. And the second layer provides the user interface functionality that is delivered through the web browser. It includes components to allow users to log in to the system and checking components that ensure that the operations they use are allowed by their role. This layer includes form and menu management components that present information to users, and data validation components that check information consistency. This third layer implements the functionality of the system and provides components that implement system security, patient information creation, and updating, import, and export of patient data from other databases and report generators that create management reports. Finally, the lowest layer, this layer, is built using a commercial database management system. It provides transaction management and patient data storage database. This is the architecture of our mental health care patient management system. We see that information and resource management systems are now usually web-based systems where the user interfaces are implemented using a web browser, as what we have seen with our example. And for example, e-commerce systems are internet-based resource management systems that accept electronic orders for goods or services and then arrange delivery of these goods or services to the customer. In our e-commerce system, the application-specific layer includes additional functionality supporting a shopping cart in which users can place a number of items in separate transactions, then pay for them all together in a single transaction. In fact, the organization of servers in these systems usually they reflect the 4 layers generic model as we have seen in the previous figure. These systems are often implemented as multi-tier client-server architectures. We see that the web server is responsible for all user communications, with the user interface implemented using a web browser. The application server is responsible for implementing application-specific logic, as well as information storage and retrieval requests. The database server moves information to and from the database and handles transaction management. So, using multiple servers allow high throughput and makes it possible to handle hundreds of transactions per minute. As demand increases, servers can be added at each level to cope with the extra processing involved. And that's for the information architecture, information systems. It's here. For this type of application is a language processing system. As we have introduced at the beginning of this section, with this system, we accept a natural or artificial language as input, and then we can generate some other representation of that language. Here in the system, we may include an interpreter to act on the instructions in the language that is being processed. And this kind of system is used in situations where the easiest way to solve a problem is to describe an algorithm or describe the system data. Here, this meta case tools process tool descriptions, method, rule 63, and generate tools. So, in fact, language processing systems translate a natural or artificial language into another representation of that language. And for programming languages may also execute the resulting code. And in software engineering, compilers translate an artificial programming language into machine code. Other language processing systems may translate a XML data description into commands to query a database or to an alternative XML representation. Natural language processing systems may translate one natural language to another, like we may translate French to English. Yeah, this figure shows a possible architecture for a language processing system for a programming language. You see here the source language instructions define the program to be executed, and a translator converts these into instructions for an abstract machine. These instructions are then interpreted by another component that fetches the instructions for execution and executes them using, if necessary, data from the environment. And the output of the process is the result of interpreting the instructions on the input data. So you see here is the architecture and possible architecture of a language processing system. Yeah, of course, for many compilers, the interpreter is a hardware unit that processes the machine instructions, and the abstract machine is a real processor. However, for dynamically typed languages such as Python, the interpreter may be a software component. In fact, programming language compilers that are part of a more general programming environment may have a generic architecture, like shown in this figure. We may include these different components: a lexical analyzer, a syntactic analysis. We may have the syntax tree, symbol table. Then we have a semantic analysis and a code generator. Here, a lexical analyzer is the function of it is to take input language tokens and convert them into an internal form. Then we have a symbol table to hold information about the names of entities, variables, class names, object names, etc. And we use them in the text that is being translated. We have a syntax analyzer to check the syntax of the language being translated. We have a syntax tree, which is an internal structure representing the program being compiled. We have a semantic analyzer to use information from the syntax tree and the symbol table to check the semantic correctness of the input language text. We have also a code generator that works the syntax tree and generates abstract machine code. This is the last component of our compiler components. Here, this figure shows that sometimes it's better to organize the system around a repository like this. Here we illustrate how a language processing system can be part of an integrated set of programming support tools. In this example, the symbol table and the syntax tree, they act as a central information repository. Tools of tool fragments communicate through them, and other information that is sometimes embedded in tools, such as the grammar definition and the definition of the output format for the program. They have been taken out of the tools and put into the repository. Therefore, a syntax-directed editor can check that the syntax of a program is correct as it is being typed, and a printer can create listings of the program in a format that is easy to read. You see, we may have different tools like editor, printer, lexical analyzer, syntax analyzer, semantic analyzer, optimizer, code generator, and they communicate or interact with this repository. Okay, here is for this type of application, the language processing systems. So we have finished this chapter, the architecture design. Now we will see the key points in this chapter. Yeah, in this chapter, we have said that a software architecture is a description of how a software system is organized. And properties of a system such as performance, security, and availability, they are influenced by the architecture used. And in this chapter, we have said that architectural design decisions include decisions on the type of application, the distribution of the system, the architectural styles to be used, and also the ways in which the architectures should be documented and evaluated. We have seen that architectures may be documented from several different perspectives, or we can say views, such as a conceptual view, a logical view, a process view, and a development view. Also, we have talked about a physical view. We have also talked about the architectural patterns. They are a means of reusing knowledge about generic system architectures. They describe the architecture, explain when it may be used, and describe its advantages and disadvantages. Here, the most common ways we use to describe architectural patterns, the tabular, it's the tabular. You see, with the tabular, we show the description, when to use, the advantage, disadvantage, etc. And we have talked about 5 commonly used architectural patterns, and we have revised at the beginning of this class the model view controller, layered architecture, repository, client server, and pipe and filter. We have seen that generic models of application systems architectures help us understand and compare applications. Compare applications of the same type, validate application system designs, and assess large-scale component for reuse. And we have normally introduced 2 types of applications. Transaction processing systems. They are interactive systems that allow information in a database to be remotely accessed and modified by a number of users. Here, information systems and resource management systems, they are examples of transaction processing systems. We have talked about language processing systems. Usually, we use these kind of systems to translate texts from one language into another and to carry out the instructions specified in the input language. Normally, these kind of systems include a translator and an abstract machine that executes the generated language. Okay, these are the key points for this chapter. Do you have some questions for this chapter? If no question for the moment, we'll continue with the 7th chapter, which is the design and implementation. In this chapter, design and implementation, the objectives are to introduce object-oriented software design using the UML, Unified Modeling Language, and highlight important implementation concerns. When we have read this chapter, we will understand the most important activities in a general object-oriented design process. We will understand some of the different models that may be used to document an object-oriented design. And normally, we will know about the idea of design patterns and how these are a way of reusing design knowledge and experience. We will also have been introduced to key issues that have to be considered when implementing software, including software reuse and open source development. Precisely in this chapter, we have these contents: object-oriented design using the UML, design patterns, implementation issues, and open source development. In fact, software design and implementation is the stage in the software engineering process at which an executable software system is developed. In fact, for some simple systems, software design and implementation is software engineering. That means all other activities are merged with this process. Yeah, these are for some simple, small systems. However, for large systems, software design and implementation is only one of a set of processes involved in software engineering, just like other processes like requirements engineering, verification and validation, etc. Software design and implementation activities are invariably interleaved. We have seen before, software design is a creative activity in which we identify software components and their relationships. These are based on our customers' requirements. In software design, implementation is the process of realizing the design as a program. In fact, sometimes there is a separate design stage, and this stage is modeled and documented. At other times, a design is in the programmer's head or roughly sketched out on a whiteboard or sheets of paper. So, design. When we design is to think about how to solve a problem. So there is always a design process. However, it isn't always necessary or appropriate to describe the design in detail using the UML or other design description language. One of the most important implementation decisions that has to be made at an early stage of a software project is whether or not we should buy or build the application software. In a wide range of domains, now it is possible to buy off-the-shelf system that can be adapted and tailored to the user's requirements. For example, if we want to implement a medical records system, we can buy a package that is already used in hospitals. It can be cheaper and faster to use this approach rather than developing a system in a conventional programming language. And when we develop an application in this way, the design process becomes concerned with how to use the configuration features of that system to deliver the system requirements. So you see, we don't usually develop design models of the system, such as models of the system, object, and their interactions. And there are a vast number of different development platforms. Here, we are not biased towards any particular programming language or implementation technology. So, here we have we are going to present our examples using the UML rather than in our programming language such as Java or Python. Yeah, we use the unified model language, which is common to all programming languages. And we don't use other specified programming language such as Java or Python. We use UML here to explain our examples. The first thing is to see an object-oriented design process. As we know, an object-oriented system is made up of interacting objects that maintain their own local state and provide operations on that state. Do you remember? This is the characteristics of object-oriented system. Can you tell me when we design the processes of object-oriented system? Normally we include normally there's a design of what will we design? Or just can you tell me what are the important elements in object-oriented system? What are the important elements in object-oriented systems? For you, what are the important elements in object-oriented systems? In your opinion, what can be these key points? Yeah, you can be referenced to our encapsulation object classes. Yeah, you got it. Inheritance. Yeah, as what we have learned before, Java, C++, C#, Python, etc. These programming languages, they have the object-oriented characteristics. You have listed many characteristics, and we'll talk about some basic one. In fact, as we said, an object-oriented system, it is made up of interacting objects, and these objects maintain their own local state and provide operation on that state. It's like the attributes, and we say that the representation of the state is private. It is like what Roy had said, encapsulation. We cannot be, these states or these attributes cannot be accessed directly from outside the object. And object-oriented design processes involving designing object classes, as said by Kaya, object classes and the relationships between these classes. These classes, they define the objects in the system and their interactions. When we realize the design as an executing program, the objects are created dynamically from these class definitions. So you see, with object-oriented systems, it is much easier to change than systems developed using functional approaches. Objects include both data and operations to manipulate that data. So we may understand them and we may modify these data and operations as standard-alone entities. Changing the implementation of an object or adding services should not affect other system objects. And because of objects are associated with things, there is often a clear mapping between real-world entities, such as hardware components, and their controlling objects in the system. In this way, we will improve the understandability and hence and also the maintainability of the design. In fact, when we develop, I said here, structured object-oriented design processes involve developing a number of different system models. And they require a lot of effort for development and maintenance of these models. And for small systems, this may not be cost effective. That's also why we say that for some small systems, software design and implementation is software engineering, and all other activities are immersed with this process. However, for large systems developed by different groups, design models are an important communication mechanism. So, for large systems, this software design and implementation is only one of a set of processes, just like other processes like requirements engineering, verification, validation, etc. Now we'll see some process stages to develop a system design from concept to detailed object-oriented design. The first stage, the first stage is to define the context and the modes of use of the system. That means we need to understand and define the context and the external interactions with the system. The second step is to design the system architecture. And the third step is to identify the principal system objects. Then we need to develop design models and specify object interfaces. You see, like all creative activities, design is not a clear-cut sequential process. When we develop our design by getting ideas, proposing solutions, and refining these solutions as information becomes available, we have to backcheck and retry when problem arises. Sometimes we may explore options in detail to see if they work. At other times, we may ignore details until late in the process. Consequently, here we don't illustrate this process or these activities as a simple diagram because that would imply design can be thought of as a neat sequence of activities. In fact, all of these activities, they are interleaved and so they influence each other. In this chapter, we will illustrate the process using a design for a wilderness weather station. We have introduced this system, this wilderness weather station system in chapter 1. We know that wilderness weather stations, they are deployed in remote areas, and each weather station records local weather information and periodically transfer this to a weather information system using a satellite link. Now we'll see a subsection of this object-oriented design using the UML. We'll see the system context and interactions as the first activity in this process. As we say that the first stage in any software design process is to develop an understanding of the relationships between the software that is being designed and its external environment. And this activity is essential for deciding how to provide the required system functionality and how to structure the system to communicate with its environment. You see, understanding of the context can let us establish the boundaries of the system. And setting the system boundaries can help us to decide what features are implemented in the system being designed and what features are in other associated systems. In this case, we need to decide how functionality is distributed between the control system for all of the weather stations and the embedded software in the weather station itself. In fact, system context models and interaction models, they present a complementary views of the relationships between our system and its environment. We'll see them in detail. A system context model is a structural model that demonstrates the other systems in the environment of the system being developed. And an interaction model is a dynamic model that shows how the system interacts with its environment as it is used. You see, the context model is a structural model, and we demonstrate the other systems in the environment of the system being developed. For the interaction model, it is a dynamic model to show the interaction between the system and its environment. In fact, the context model of a system may be represented using associations. Associations, as we have used, I think in the last semester, we have used associations in Java. With associations, we can simply show that there are some relationships between the entities involved in the association. And the nature of the relationships is now specified. We may document the environment of the system using a simple block diagram to show the entities in the system and their associations. Here, this figure, as shown in this figure, you see we use some simple block to show the entities and relationships or associations. This figure shows that the system in the environment of each weather station are weather information system, a onboard satellite system, and a control system. The cardinality information on the link shows that there is one control system but several weather stations, one satellite, and one general weather information system. So you see, when we model the interactions of our system with its environment, we should use an abstract approach. Yeah, here it's for the system context. But if we want to model the interactions of our system with its environment, we need to use an abstract approach that does not include too much detail. And one way to do this is to use our use case model. Yeah, as we have discussed in the chapter 4 and chapter 5, each use case represents an interaction with the system, and each possible interaction is named in our ellipse, and the external entity involved in the interaction is represented by a stick figure. It's like here, this figure shows the use case model for the weather station. And this shows that the weather station interacts with the weather information system to report weather data and the status of the weather station hardware. Other interactions are with a control system that can issue specific weather station control commands. As we have said in the previous chapters, a stick figure here is used in the UML to represent other systems as well as human users. So you see, each of these use cases should be described in structured natural language, and this helps designers identify objects in the system and gives them an understanding of what the system is intended to do. So here we use a standard format for this description that clearly identifies what information is exchanged, how the interaction is initiated, and so on. Yeah, you see here we have a tabular description to describe the report weather use case from this figure, from this this figure. Yeah, we see that you see the same structure of the tabular use case, actors, description, stimulus, response, comments. It is a system, weather station system, and we have the use case, the weather, the report weather. Actors, we have two actors. We have the weather information system and the weather station. And the description of report of this weather station is that the weather station sends a summary of the weather data that has been collected from the instruments in the collection period to the weather information system. The data sent are the maximum, minimum, and average ground and air temperatures, the maximum, minimum, and average air pressures, the maximum, minimum, and average wind speeds, the total rainfall, and the wind direction as sampled at 5-minute intervals. The stimulus is that the weather information system establishes a satellite communication link with the weather station and requests transmission of the data. The summarized data is sent to the weather information system. And weather stations are usually asked to report once per hour, but this frequency may differ from one station to another and may be modified in future. You see here, this description is for the report weather use case of this figure. Yeah, here, so till now, we have talked about the system context and interactions, which is the first step to develop a system design from concept to detailed object-oriented design for design implementation. You see, in this first step, we need to classify the system context model and the interaction model. We have said that with system context model, we can use simple block diagrams to show the entities in the system and their associations. For the interaction models, we can use use case models. We can use case model to show an interaction with the system. We can also use the tabular to describe the system in detail. Okay, this is this part, and the next class will continue with the second stage, which is the architectural design. If you don't have some questions for the moment, perhaps we'll stop here and we'll continue the day after tomorrow.